Thanks, everyone, so much for coming out for my second talk at Black Hat this year. Today, I'm going to be talking about the Secure Boot security story, what Microsoft has been doing, and also what we're going to be doing to fix it. Let's get right into it. So my name is Bill Denberg-Kuppa, and I work for the Microsoft Security Response Center as the Emerging Threats Lead. I have a background in cloud security and low-level OS internals, and I've worked with Secure Boot for a little over a year now. I'm going to first start by telling you a little bit about what Secure Boot is, and then we're going to move into some of the challenges that we've been facing with it. So the UEFI Unified Extensible Firmware Interface is an industry standard that came after BIOS or legacy boot in order to unify the practices of how your firmware is designed and what interfaces it offers to developers. So there's a lot of benefits with UEFI, including larger drives. The unification leads to a better developer experience, but it also has better security. So for example, BIOS really only had an access control using a password commonly available, but with UEFI, we have something called Secure Boot, which actually guarantees the validity of any code being executed at boot. The challenge with UEFI Secure Boot is, how do we know what to trust? How do we know what code is allowed to load in the first place? So UEFI runtime variables are how the OS and firmware can interact with each other, and including your OS boot environment. The UEFI runtime variables include your boot order, what is going to load first on your system. But it also includes the signature list variables, including the key exchange key, platform key, the allowed signatures list, and the denied signatures list. So the way that Secure Boot defines trust is through these variables. Images are signed by a certificate in your allowed signatures database, DB. And then to modify DB, you actually need to have a key exchange key signed payload. And to modify the key exchange key, you need to have control over the platform key. And finally, to revoke trust, when something goes wrong, we use the denied signatures list, known as DBX. The really interesting part about DB and DBX, and also the other certificate variables, is that they're authenticated. So they control what you can load and allow hashes or certificates. So I can include a hash of an image that I want to allow to load on my machine, or I can load the Microsoft CA, for example, into DB, and that'll control any Microsoft image will be allowed to load. By default, the certificate authorities that come with a default Windows machine include the Microsoft Production CA and also the UEFI third-party CA. And another interesting fact about these authenticated variables is that they're almost always append-write updates. So instead of rewriting the entire allowed signatures list or rewriting the entire deny list, what happens is we can sign payloads that will instead merge with what's already there. This way, if you have any custom revocations, maybe by your OEM, you're not going to be losing those whenever Microsoft issues an update. Now, DBX is really critical to Secure Boot because Secure Boot needs to stop unauthorized code, but it's not just stopping unsigned images. If there's any vulnerability in a UEFI image, we need to make sure to revoke that image so that the legitimately signed image can't be abused in the future. And so DBX is actually how we're able to revoke the trust of previously signed images. The reason it all matters is because Secure Boot is what keeps your boot environment secure. It's critical for establishing a chain of trust. It deters physical attacks substantially, and it prevents malicious code from executing at boot. Features like BitLocker, for example, leverage Secure Boot as a part of its security story. So I'm going to tell you a little bit about its threat model. Windows has several security boundaries that are defined on the Microsoft website, which are logical separations between the code and data of different trust levels. A boundary, as an example, would include a non-admin user can't escalate their privileges to kernel code execution. And an example of a non-boundary would be an admin user that can execute kernel code. Secure Boot is not a security boundary, but it is a security feature that we intend to service. So the real problem with Secure Boot that we've experienced is the attack surface that comes from including administrators in its threat model. In almost all other Windows components, admins are usually out of scope because admins are assumed to have a high level of privilege. Secure boot is one of those exceptions. So when you start up your machine, there's a lot that happens. On the right, I have a high-level overview of the different components that go into your machine's boot environment. So when you power on your device, the firmware will load any option ROMs or drivers needed to support your hardware, and your OS bootloader will actually initialize the environment for your operating system. But the challenge here is that every single step of the way is another attack surface that attackers can take advantage of. And it makes it very difficult when UEFI, everything is attack surface in UEFI. So to dissect this a bit further, we have the firmware challenge, where everyone has their own fork. The updates are often decentralized, and there's an unverifiable supply chain. We'll talk about this briefly later, but the serious problem with the firmware issue is that you can have one shared code base that'll have 1 million vulnerabilities, and the next thing you know, any fork of that shared code base will also have those vulnerabilities. Making sure that vulnerabilities are fixed when the entire ecosystem is decentralized in nature is a really challenging problem that can leave users exposed. Another factor for risk includes the disk. So this is why we need to have DBX in the first place. You can't trust any file as a UEFI developer. For example, an attacker can bring an old version of a bootloader that has a vulnerability and then swap out your bootloader with this vulnerable one. This is why it's so critical to have the capability to revoke trust, not just assign it. And to make matters worse, these file systems can actually be remote as well. Another layer of risk includes Microsoft images. So these are images that Microsoft signs to enable, for example, Windows. Now, these images can have often a lot of unaudited attack surfaces. There's by design risks where sometimes for extensibility, a feature is added to these bootloaders that allows you to do things that might compromise our security model. And to be clear, the Microsoft image store is also exposed to third parties by default. And third-party images that we sign with the UEFI CA, so this includes things like Linux, well, we have over 15,000 of them. And the problem is we often have a lack of visibility into these images. We are given a binary blob that we can go ahead and sign, but sometimes we add a questionnaire. Other than that, it's really difficult to know what makes up these different drivers. And every single driver here is another by default attack surface. Like Microsoft images are exposed to the third-party customers, third-party images are also exposed to first-party customers. So where do we draw the line in terms of what we consider defensible? Well, in general, an admin user that can compromise the boot environment is something we're going to want to address. Now, for physical attackers, it's usually defensible. Obviously, with enough time and effort, chances are secure boot can be compromised. Network boot to the boot environment is also another example of something we'd like to defend. But unfortunately, network boot to user mode is not something that we consider defensible. So for example, there's a lot of features that we've added for administrators. Like let's say I want to deploy a custom image for my organization. In these cases, if you can achieve the same impact by design, then unfortunately we don't consider that something we want to defend. Now let's talk about what makes secure boot so difficult to defend in the first place. Number one is our limited response capability. Remember, to fix UEFI bugs, we not only need to fix the code, but we also need to make sure to revoke every image that had the vulnerable code in the first place. So the UEFI standard says to add these images to the DBX variable, like we talked about earlier, but this variable only has 32 kilobytes of space on Windows 10 machines up to the hardware requirements for 1709. This equates to roughly 600 to 800 unique hashes, and while that sounds like a lot, it's a lot less than you might expect. Right now, we're actually at already halfway filled with the DBX variable, and it's a problem for us because there's a lot more vulnerable images we need to consider. And finally, revoking isn't always going to be possible. For example, even if we had all the space in the world, sometimes it's really difficult to revoke because what if I have Windows on a USB stick and that bootloader has vulnerable code in it? Now, if you plug in that USB stick, you're not going to be allowed to load your USB. Imagine that in a recovery scenario. It would be a disaster. The different certificate authorities in play here include the production CA and the third-party CA. So with the production CA for Windows, that includes a lot of extensible features, products, etc., and that's over 10,000 boot images that we've signed. And the third-party CA, like we talked about, includes over 16,000 boot images that we've signed to date, and that's a lot of unaudited attack surface that can share code and cause problems. Now, will all 30,000 signed images from both CAs have vulnerabilities? Probably not. It's hard to be safe in UEFI when everything is an attack surface. A vulnerability in one image is rarely limited to that one image. For example, if you have a shared library in one image, that library might be compiled into a bunch of bootloaders that you sign. And now if there's a vulnerability in that library, we have to go ahead and revoke every single image that has that library and every previous version of those images that also had that library. This is where the DBX failures come into effect. It's great in theory. I completely agree with it in principle. But in practice, 600 to 800 hashes is not much space at all. So to go through some examples, to start with Windows, some of you might be familiar with Black Lotus. So ESET published a report about Black Lotus, an end-of-wild bootkit, a little over a year ago. And the interesting part about this vulnerability was that it abused CVE 2022-21894, which was actually fixed in a previous security update. But how are they abusing it? Well, the blog is great. I recommend you check it out. But from a high level, it ran into the problem of, even though we fixed the latest version of the code, what we didn't do was revoke in time. So the DBX variable didn't have every boot manager because, simply put, there's too many boot managers with this shared code in it. Unfortunately, this means that an attacker can bring an old vulnerable bootloader and swap out the existing one in order to compromise your machine. Now, to be clear, this still requires administrative privileges. An attacker would need to have physical access to your device, or they would need to have admin code execution, which is what Black Lotus was using. But it still presents a risk because it compromises the integrity of your boot environment. So to recap, fixing vulnerabilities isn't just enough. We need to revoke those vulnerable images too. And one bug can equal thousands of executables. We released an opt-in mitigation for Black Lotus to help reduce some of that end-of-wild abuse. It isn't perfect, but we're still working on a default secure revocation story. So the challenge here is not only that it's going to introduce compatibility issues with everyone that has an old Windows image on, let's say, a USB stick, but it's also about that space issue. We don't have enough space to enforce revocations for every bootloader that has been signed up to 2022. If you're interested in learning more, you can check out the link about this CVE online. Now, going to the UEFI CA, let's talk about the Linux shim. The Linux shim is a first-stage bootloader for effectively every distribution that supports secure boot. And it's designed to effectively manually load secondary drivers like RUB by verifying them and mapping them into memory. And the way it works is that the shim actually contains the Linux distribution certificate. So the Linux distribution signs their own images, and then they include the certificate in the shim, which is signed by the UEFI CA. And this allows them to sign their own images in the future and load it using the shim. Now, MSRC was actually able to find a critical vulnerability in this code that has been public for nearly a decade. It allows attackers to execute code from a remote scenario, a local scenario, a physical scenario. Now, it was fixed in January 2024. You can see the CVE issued on the right. And the code was out, but unfortunately, the revocation date is still unclear in a lot of cases. Remember, just because we fixed it in the latest version of the code, that doesn't mean we're safe. Now, Linux doesn't even need DBX. They have a custom revocation scheme known as Secure Boot Advanced Targeting. This allows them to target revocations by version instead of using a hash or certificate in DBX. But unfortunately, SBAT, as it's called, is an unauthenticated variable, which can allow tampering. And even with SBAT, they're not able to revoke. Why? Because there are just too many users with the old shims. So to recap this challenge, the revocation challenge is an ecosystem problem. For some, it's about not having enough space to issue those revocations. But for others, it's about breaking legitimate use cases. UEFI exposes an enormous attack surface and then expects developers to shoot themselves in the leg to fix it. And this is why it's so hard for defenders to be able to respond to these types of vulnerabilities, is because, again, that space challenge, that we're not working with a great system. And number two, in reality, the revocation story becomes a lot more complicated due to that compatibility risk. Now, number two problem I want to talk about is the substantial attack surface. So the attack vectors from the threat model we reviewed introduce enormous risk. In UEFI, almost anything configurable is an attack surface. Every feature in every boot image is more surface for attackers to take advantage of. For the UEFI CA, we have over 16,000 signed but unaudited boot images. And now sometimes these use cases are justified. For example, Linux is a critical part of our ecosystem. They're never going away. Option ROMs are often necessary for modern hardware. For example, your graphics card comes with what's called an option ROM in order to support your display. But sometimes we've seen less justified use cases for the UEFI CA, like debugging-related images, including UEFI shells, that expose dangerous behavior by design. And also, to be honest, there's a lot of random utility that no one really uses. And it's not that we shouldn't sign these in the first place, but it's just that should we really expose these surfaces by default? We should be able to support these competitive use cases, but that by default exposure is what really concerns me. Now, for Windows CA, even though it's only first-party code, Windows is one of the largest operating systems. Inherently, it has a lot of different features for extensibility, and again, you start to wonder how many of these features will customers really need by default? So the big question that I would like to really reinforce with this problem is that a vast majority of attack surfaces won't be relevant for a vast majority of customers. Does every single Windows computer in the world need to be able to run Joe Schmo's disk recovery utility by default? Do all Linux users who just want to use Linux really need to be exposed to Microsoft's attack surface by default? So to go through some examples of this, I want to start with Windows boot code. Now, I'm going to go through a few high-level examples of what vulnerabilities we've seen in the boot manager look like, but I'm not going to spoil the findings of other researchers for you. Without our community, we wouldn't be here. It's really important to have that accountability, and we greatly appreciate the support in helping secure our boot environment code. So one really big pain point for us has been the boot configuration data, known as BCD. So this BCD file has everything from whether you should start in safe mode, are we going to start in recovery, where is the OS loader located, what about the NTOS kernel? Now, these BCD options, we have over 100 of them. That's a lot of different attack surfaces. So we've actually seen about 50 or more MSRC cases in just BCD parsing alone. And that's a lot of attack surface. So I want to show you what some of these issues look like. So a common pattern that I've seen is that developers can easily forget everything that is configurable is untrustworthy. On the right, I have a function that's a copy, a mimic of a real vulnerability that was discovered. And from a high level, what it does is it'll first grab a device from your BCD file, and it'll store it on the stack. Now, this device actually has a custom structure, and this custom structure contains information specific to that device, but you have to remember everything here is untrusted. And finally, here's where the bug comes into play. It'll allocate space for a copy, but it assumes a certain set size. And when that allocation is done, it'll copy over the custom device information into this new device information that was just allocated without verifying that the size specified by the attacker is actually legitimate and within the bounds of what's expected. This leads to an out-of-bounds write condition. And another major threat for boot code is extensibility. So, for example, did you know that the Windows bootloader, by default, can expose over 10 different file systems? It's a fuzzer's paradise, to be honest with you. This includes everything from NTFS, which makes sense. A lot of people use NTFS by default. But there's also just these random edge case support that really makes you wonder, well, a lot of customers need this by default. Well, should they really be exposed to these surfaces by default? With the UEFI CA, MSRC actually reviewed a large set of these images manually, and we found a lot of trivial problems. We're going to go through a few examples really quickly, but if you're interested in learning more about the third-party story, I definitely recommend you check out Dissecting the Third-Party, Secure Boot's Third-Party Attack Surface, which I presented at OffensiveCon a few months ago. So one example that I covered there includes the fact that there's a lot of unrevoked images that are variants of previously revoked images, which attackers can abuse. So one trivial path was, let me just search for similar images to ones that have been revoked and find those images which are maybe a slightly older version of what was revoked that still have the same vulnerable shared code. Remember, when you revoke an image, you not only need to revoke the latest version where that vulnerability was found, but you also need to revoke every image that had that code in previous versions. Another challenge is, for example, even the Linux shim. It's designed to load arbitrary boot code signed by individual Linux distributions. We don't have a direct audit log or visibility, but MSRC was able to recover some of these images using VirusTotal and their signature filtering mechanisms. For example, Fedora actually used the same certificate, their self-signed certificate, from 2012 to late 2013. And this allowed attackers to abuse vulnerabilities from 2015 to 2020 because they didn't roll their certificate. And remember our shim vulnerability that we briefly discussed in the last problem? Well, I want to go through that example because it highlights the extensibility issue. On the right, I have an HTTP response handler that'll first parse a content length header from the server, and then it'll use this buffer size from the server to allocate a pool. And finally, it'll copy over the number of bytes sent by the server over to this buffer. And this is where the problem arises. Because the content length is untrusted, and it's from an untrusted server, there's nothing stopping the server from lying to you and saying, oh, the content length is only 1 byte. But in reality, I'm going to send you 1,000 bytes. This again goes back to the idea of extensibility. Extensibility can add attack surface and increase customer risk. So to recap, it's really hard to write secure code for UEFI where everything is an attack surface. The status quo includes an enormous amount of by default attack surface that users will probably never need. And balancing customer choice with security is not trivial. The third problem is going to be an inconsistent industry response. So users are only as secure as the weakest link. How can Microsoft maintain a strong security story given partner-introduced risk? We've seen an inconsistent commitment to customer security in the ecosystem, unfortunately. Like some partners, like the Linux community, take security extremely seriously, but others not so much. I talked about this in my last talk, but for example, the firmware story, there's a lot of risk that can be introduced by the shared code and decentralized nature of firmware. Let's say you have a vulnerability in your component supplier, that can easily become a vulnerability in variants of that image too. And this leads to a lot of known vulnerabilities that can be abused against your organization simply because your vendor hasn't taken the necessary updates. This was research done by Binarily, and what we can see here is that in order to abuse this problem, attackers can first dump your firmware, find out what you're running. They'll find a version and look for that repository online. A common one is EDK2, which is the firmware source code repository, pretty commonly ingested by different OEMs. And they'll just enumerate known vulnerabilities in EDK2 in order to find new issues they can abuse against your machine. Even though these issues have been patched upstream, that doesn't mean they've been ingested by your downstream vendor. If you're interested in reading more, I'd recommend you check out Binarily's blog post on this. And unfortunately, there are dozens of fixed boot vulnerabilities abusable by a rollback attack. That's what we were talking about with Black Lotus. So why haven't we revoked those old versions? Unfortunately, revoking means blocking every first-party image we've ever signed. Good news. We've actually been planning to revoke and roll the Windows CA in 2025 and 2026 period. And why haven't we expedited this process? I have an excerpt below from a blog post about this roll process, and it discusses some of the challenges at a high level. And what I really want to call out about this paragraph is that last sentence. Microsoft will slowly roll out this DB update as we validate devices and firmware compatibility. The reason we can't just do this tomorrow, it's going to help revoke a lot of these old images. Why don't we roll the Windows CA tomorrow? Well, it turns out, with that last sentence, there's a lot of issues that can be introduced from partners. So what we found was that with these new additions for rolling the CA, Secure Boot can actually brick entirely. So can you imagine a security fix breaking your machine, especially for Secure Boot? This is why it's so careful. We have to be so careful with these changes to make sure that we're prioritizing customer security, but while we bring customer reliability along with us. And to be clear, this is an industry-wide challenge. One thing, for example, Microsoft needs to do better here is going to be allowing partners to have access to better testing tools to catch these types of issues earlier rather than later. And going back to the OEM risk, I want to talk to you about the platform key, which controls the key exchange key and controls the allowed signatures allowed to load in Secure Boot. Many OEMs choose to manage their own keys, but unfortunately, they're not always maintained. So on the right, I talked about this more in my last talk, but for example, there are a lot of OEMs that included an old version of a canonical certificate. And this version has been used to sign really old code with several known vulnerabilities. And this certificate is still included in some OEMs' firmware by default today. Another funny one that I saw really recently, a few weeks ago, includes some research from Binarily where they found that a lot of OEMs have a PK, a platform key named Do Not Trust AMI Test PK. This AMI test key was stored in a private key file included with UEFI test packages. And with PK, remember, you can bypass Secure Boot by updating the key exchange key or the allowed signatures list known as DB. If you're interested in reading more about this one, it's a really interesting one. I'd recommend you check out their article named PK Fail on Trusted Platform Keys Undermine Secure Boot. So to recap, Microsoft needs to work with partners and will work with partners to challenge the status quo of UEFI. We all have problems here. Microsoft has several things that we need to address, like Black Lotus, but we also need to make sure we're looking at the full picture. UEFI is not going to be something we can solve alone at all. We're going to need to bring partners along with us, and we're going to need to work on this together. Now, I will say the decentralized nature of the ecosystem presents a severe threat to customer security. Especially with that firmware problem, it becomes really tricky because when there's known vulnerabilities, we need to make sure that they're promptly addressed across the board. We don't want to leave customers vulnerable. And just to really reiterate one of our big points, it's about balancing customer choice with security. It's a really interesting and difficult challenge because we want to allow choice. We want to allow our OEMs to bring their own security solutions, for example. We want to allow the UEFI CA. We want to allow those third-party use cases like even Joe Schmo's disk recovery utility. But at the end of the day, users are only going to be secure as the weakest link. So let's talk about how we're going to fix it anyways. So while a decentralized ecosystem is great for customer choice, it's not so great for customer security. I think that the industry response time inside of UEFI can highlight this inefficiency. UEFI might be a unified interface, but we need unified execution. So from a high level, if you're an OEM or a partner of us, I'd recommend that you look into using Windows updates for deploying your UEFI firmware updates. A lot of them are already doing it, but if you're not already doing it, I'd recommend it. Because honestly, no one's going to go to your website. Maybe 5 people will, but not many at all, to take a firmware update in the first place. If you want to keep your customers secure, and I know you do, we need to do it together. I think that we need to collaborate more on secure implementations and try to get away from the forking problem. So stop creating forks of these shared code bases, especially the larger ones with a lot of attack surfaces, because what will happen is that it's really hard to manage security when you have so much code, when there's so much shared code bases, and when there's so much attack surface. It's not just about forking being a problem because it introduces security risk, but it's also because it's a lot more work for our partners to be able to manage it effectively. It's just more liability. And if we can combine some of these implementations together, we can help improve the customer security story while reducing the cost for this maintenance. I think we need to invest more in firmware transparency and auditability. There's a lot of the problems we've seen is from a lack of transparency into the firmware. How do I know if my firmware has the latest update for EDK2, for example? So talking about a bit future-facing things here, number one, how do we empower partners to value customer security the way we do? Well, I think that, first of all, we need to prioritize customer security first, security above all. But we need to make sure to bring our partners along with us. So partners who are prepared for our rollouts will be added on an ongoing basis, and customers will receive protection as soon as feasible, rather than waiting for complete participation. The intent here is to make sure that we're securing customers where we can, when we can, and making the security story better as we go along. I also want to tell you about Secured Core, which is a way you can reduce your attack surface. It's a special line of Windows computers that have strengthened defaults. Now, on laptops with Secured Core, the UEFI, for example, is not included by default. You have to enable it in your firmware options in order to have that option available. You can see that down below, where we state that the third-party UEFI is not trusted by default with a BIOS option enabling that trust. And the really interesting part about this is, again, it's not that the UEFI is bad at all. We need that customer choice. But the UEFI is an interesting attack surface that attackers can take advantage of, and the real question is, should we have that exposed by default? Secured Core is one way you can make sure that it isn't. Now, I will say for Secured Core, if your machine requires option ROMs, there are some exceptions to this requirement, but it still offers at least a choice to help reduce that attack surface on your enterprise devices. So what are we going to do about DBX? That was another really interesting problem. Well, I want to tell you about a really interesting implemented proposal, which is revocation through secure version information. So this was an MSRC design to extend DBX and allow revocations by version. So for example, Linux has Secure Boot Advanced Targeting, but Secure Boot Advanced Targeting takes advantage of an unauthenticated UEFI variable. And the reason that's a problem is because if an attacker can get code execution at boot, they can just delete your variable with your revocations, and you still remain unprotected. Whereas with DBX, the really cool part about it is that it's an authenticated variable. So this means that if an attacker got code execution at boot, that wouldn't allow them to tamper with DBX. So what Microsoft found was that we can actually use DBX in order to store ththese version revocations. How it works is that we have 32 bytes of space with a SHA-256 hash, and what we came up with was including version data inside of a fake hash that we would then add to DBX. This way, our code would be able to recognize this pattern and derive version information from an entry in DBX. We'll still run into the space limitations that DBX has, but now with a single hash, we can actually revoke thousands of images by version. So the way this works is that the signature owner field in the signature list header will include a specific GUID that our code recognizes, and the signature data is the fake hash with version data in it. The cool part about this is that for anyone else who parses DBX, this is just going to look like another random hash. But for our code, we'll be able to recognize it as, hey, this actually contains version data. This implementation was actually released in April. If you have your April security update, you will have this code on your machine today. Now, we will still need to revoke the old Windows CA in order to really take advantage of this mechanism, but I want to demonstrate Microsoft's commitment to customer security here. It's something that we're continually improving on, and it's something that we're interested in helping partners achieve as well. Another implementation includes support for Linux revocations. Remember the Linux shim and a lack of revocations? So a Patch Tuesday in the next few months will actually include revocations for the Linux vulnerability we talked about. Now the revocations are SBAT, so Secure Boot Advanced Targeting, and that were provided by the Linux community in their shim repository. And to be clear, we also still care about the compatibility story. If you're dual booting Linux, these revocations won't apply to you. I would recommend that you check out your device in a few months to see this take effect. And one thing I really want to emphasize again is that Microsoft is not going to do this alone. So first, we're going to partner with the research community to hold us accountable and identify problematic attack surfaces before we have years of investment in them. We want to partner with OEMs to share the right tools to help balance a secure outcome and compatibility. So this means, for example, that issue I talked about when we were trying to roll to CA, one of our partners' machines were bricked. Well, Microsoft will make sure to offer better testing tools to try to detect those types of issues before it's too late. We also want to partner with other organizations like CISA to help push the industry in the right direction. And finally, we want to continue partnering with our Linux community to maximize choice without forgetting security. And one area we didn't cover in this talk was measured boot, which uses the trusted platform modules to protect important secrets behind trusted measurements. And BitLocker is a good example of this. If you use BitLocker on your machine and you have a TPM available, it'll actually use these measurements to protect your disk keys. But unfortunately, BitLocker is not used by the majority. And it's only really going to be effective against physical attacks today. For example, Black Lotus, one of the things it does is if it detects BitLocker on your machine, it'll suspend protection. And the reason it's able to do that is because BitLocker was designed to originally address physical attacks. If you already have access to the unlocked disk, BitLocker is about protecting your data. If you already have admin code execution, what data is there left to protect? But we still have longer-term investments like dynamic root of trust for measurement that are really promising and for the future. So today, if you use DRTM on some of our newer devices, for example, Black Lotus won't work by default. Now, there are still changes we need to make for DRTM to make it reliable in the long term. For example, even if DRTM is able to detect tampering, we need to make sure that we put enough stuff behind DRTM so that an attacker actually needs to pass DRTM's detection system. So for example, if DRTM fails attestation, that doesn't prevent your machine from unlocking BitLocker keys because that BitLocker hasn't been added behind DRTM just yet. But again, this is something really promising that I look forward to in the next 5 years as a way to really mitigate these secure boot security story problems. So what can you do to protect your organization? Number one, if you want to help protect against physical attacks, you can use BitLocker. This, again, uses measurements to make sure that when your machine starts up, you're booting into a trusted environment. Now, if you want maximum security, I definitely recommend that you use TPM and PIN for really making sure that even if there was a vulnerability in a BitLocker image, your data is going to remain safe because they don't have your password. We can use secured core PCs to reduce third-party attack surfaces is another one. Now again, option ROMs are going to be a problem, and secured core will only really reduce your third-party attack surface if your machine is a laptop and doesn't have that option ROM exception. I definitely recommend that you apply the opt-in protections from Microsoft if these boot attacks are in your threat model. And if you're really interested in getting the maximum security, you have money to throw away, and you want the best of the best, you can opt into managing your own certificates. This means that instead of relying on Microsoft to manage your DB and DBX variables, you can just have a very small set of hashes that are allowed to load. The NSA actually has a great guide on customizing the secure boot environment. But it should be noted that this is going to be a lot more costly than some people might expect. So just to conclude this presentation, the really big message that I want to emphasize to everyone, if you have one takeaway, is that I think that we as an industry, we can often fall into the trap of focusing on short-term fixes. But really what we need is to rethink secure boot. Secure boot needs an overhaul to remain defensible. We're doing our best with what we have. Our partners are doing their best with what they have, the limited resources. And what we're really looking at is a system that ties our hands behind our back. And above all else, we need to do this together. Thank you so much for coming out to this talk. I'm really excited to be here again for another year. And thank you to all the engineering teams and partners who are helping improve the customer security story.